Good morning. This is Sunday, it's September 11th, and we are moving into week 3 of our online astronomy course. Hope everything is going well for you. I hope you're enjoying this cooler weather we're having. I could do without the smoke in the air, but I hope that will be blown out of here pretty soon. But welcome to week 3 of online astronomy. Now, remember that all astronomers can do is look at the stars and look at things in the sky, like from objects in the sky, stars, planets, moons, and so on. And some of those move from night to night, like we found out that the planets move against the distant background stars from night to night. The moon moves across through the stars from night to night. And over a period of years, other stars, about half the stars in the sky are binary stars, that is, two stars, or maybe even more, that orbit each other, move around each other, the way planets orbit the sun. And we've also seen that other planets have moons around them as well. That's all we can do is watch that happen. What can that tell us? Well, to understand what their motions can tell us, we have to go back to a man who was born in 1642 in this house that's right here behind me. It's in Woolsthorpe, England, and that man was Isaac Newton. It's Isaac Newton who really figured out how things move. And he is celebrated for his 3 laws of motion. 3 descriptions that say how things move. And the first law simply says that things at rest stay at rest. If I have a book lying on the table, it stays there. Or objects in motion remain in motion. If you watch a bowling ball rolling down an alley, you let go of it and it just keeps going. And he say they move at a constant speed in a straight line unless an unbalanced force acts on them. Now, this may seem really simple, but it was revolutionary because people used to think that you have to keep pushing on something to keep it moving. But Newton says, no, 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 no. He says motion is natural. Motion is a natural thing. And what forces do is that they cause a change in motion. So, first of all, what is a force? What is a force? Well, it's just a push or a pull. So if you push something or you pull on it, that's a force. So forces cause changes in an object's motion. Unbalanced forces do. Now, what sort of changes in an object's motion can we have? Well, something could speed up. It could slow down. Or it could change direction. And all 3 of those count as a change of motion. And so we call all of those by the same name. We call them an acceleration. So an acceleration occurs when an object speeds up, slows down, or changes direction. Now, in everyday English, we use acceleration for speeding up and deceleration for slowing down. But no, in science, we toss deceleration out the window. We don't need it. So any change in motion, speeding up, slowing down, change in direction, all of those count as an acceleration. So here's what happens. An unbalanced force causes an object to accelerate, speed up, slow down, change direction. Now, what do I mean by an unbalanced force? Well, let me give you an example of that. I have a little box here, you can see. I'm just going to hold that. I'm just going to place that. My hand is like a table. Now I'm just going to place that box on the table. And the box isn't moving. Now there's forces acting on the box, right? There's the upward push of my hand, and then there's a downward pull of gravity. And if I took gravity away, the push of my hand would send that box way high. And if I pulled my hand away, then that box would fall, which it did. But right now, those two forces are in balance. That the upward force of my hand is balancing the downward force of gravity. And so the box remains at rest. But if there is an unbalanced force acting, then the object's motion change. And that's why if I have a block, I try to push that across the floor, it won't go at a constant speed, it will slow down because of the unbalanced force of friction between the block and the floor beneath it. Friction is just a rubbing force that opposes motion. And so if you just are trying to keep something going, like if you're in a supermarket and you're pushing on the cart and you have to keep pushing to keep it going, that's because your push is balancing the force of friction on the wheels that's opposing the motion. And when those two forces, your push and the backwards opposing force of friction, when those are in balance, the cart moves forward in a straight line. If you push harder than the friction, the cart will speed up. And if you push slower than the friction, the cart will slow down. And in those two cases, either one, if I push harder or if I push weaker, then there's an unbalanced force and the cart's motion changes. So that is Newton's first law. An unbalanced force changes motion. His second law, Newton's second law, talks about how much acceleration you get when you push on something. Now, the force just can't determine the acceleration, right? Because if I push on a ping pong ball and I push on a bowling ball with the same force, that bowling ball is going to change its motion much more slowly. It's going to speed up over a longer period of time than if I just push a ping pong ball with the same force. So what's the difference between the ping pong ball and the bowling ball? And the answer to that is their mass. Now, mass is just a measure of the amount of matter that's in an object. A bowling ball has a lot of mass. Ping pong ball has very little mass. And so if I use the same force on the bowling ball and on the ping pong ball will accelerate much more because it has a smaller mass. You can think of mass as an object's resistance to having its motion changed. And in fact, an object's resistance to having its motion changed is sometimes called inertia. But we'll just use the term mass because that's what inertia is. It's mass. So here's what Newton's second law says. It says that if I push with the same force on the same mass, I get the same acceleration. If I push with twice the force on the same mass, I'll get twice the acceleration. Sure, if I push twice as hard, it speeds up twice as much. Makes sense. Now, Newton's third law is one that's sort of counterintuitive. And you have to think about it. If you've ever been, for instance, in a city that has a subway like New York, and the train pulls up and you're trying to get in and people are trying to get out and everybody's pushing against each other. You push on the person in front of you and they push back on you. Well, that's what Newton's third law is all about. And it says that if I push on you, you push me back with the same strength force, but in the opposite direction. So I push on you, you push on me back with the same strength force, but in the opposite direction. And you can demonstrate this for yourself. All you have to do is take a rubber band, like I have here, rubber band, hook it around your thumbs, and stretch it out. And you'll see that you feel the same strength force on your thumbs. And no matter how you change the stretch, how you move your thumbs around, that force on the thumbs is always the same. And so that's what Newton's third law says. I push on you, you push back on me just as hard. So Newton is celebrated for those three laws. His three laws of motion were actually the beginning of our understanding of the physical world and how it moves. But that's not all. Newton also described why the moon orbits Earth and why an apple from a tree will fall to the ground. And supposedly, the story goes that Newton was sitting in his house, and he was sitting looking out through this window right there at his apple orchard. And then when I was here visiting in, when was it, 2012, I just happened to stop by his house, and Newton looked out that window, and according to the story he told, he saw an apple drop from the tree. Now, there's lots of apples around Newton's house, lots of apple trees. This one behind me right here is the apple tree that Newton saw the apple fall from. It's a historic English tree. There's a plaque right by it, and it's lived ever since Newton's day. Newton was born in 1642 on Christmas Day, actually, and that tree has been there ever since, still producing apples. But Newton was the first person to realize that the same force that caused an apple to fall to the ground is the same force that keeps the moon in orbit around Earth. Newton realized that every object that has mass attracts every other object that has mass. So if you just hold up two rocks, those two rocks attract each other by their gravitation. Each rock attracts the other. And that goes for everything around you. You know, if there's a person next to you in the room, or if I was next to you, you know, I would attract you, you would attract me, just because of our masses. But what are we most attracted to of all things? We're attracted to the thing that has the most mass, and that is right under our feet. That is the Earth. And so it's the Earth's attraction on our mass that causes us to be pulled down to Earth. And the Earth's attraction by gravity to everything that causes it to be held onto the Earth. And the Earth attracts the moon and holds it in its orbit around Earth. And you might wonder, well, you know, why isn't the moon just pulled down to Earth? Well, you know, if the moon, if my fist is the moon, and I'm sorry, if my fist is Earth, and here's the moon, if the moon were still, yes, it would fall straight down and collide with the Earth. But the moon also has a sideways motion, and that sideways motion carries it around the Earth. And so the moon is continually falling around the Earth. Same thing for astronauts in the space station. They are continually falling around the Earth. They haven't escaped the Earth's gravity. There's gravity up where they are. But it turns out that everything falls in the same way. If I have a heavy ball and I have a little light ball, and I drop them at the same time, boom, they'll hit the ground at the same time. That is, if I neglect air resistance. And in the videos for this module, there's a picture of an astronaut on the moon, and he has a hammer and he has a little light feather, and he drops them at the same time, and they hit ground at the same time. So the astronauts in the space station are all falling side by side, along with their spaceship, their spacecraft, around the Earth. And they appear weightless, but weightless really means that they are falling freely under Earth's gravity. So, wonderful information we can find out, because as we watch objects orbit each other, we can find out their masses. Newton's law of gravity, plus his laws of motion, first of all, completely explain Kepler's laws of motion. Why do the planets orbit the sun in an elliptical orbit? Why is the sun at one focus? Because of Newton's laws of motion. They explain it perfectly. Why do planets sweep out equal areas in equal times? And Newton's laws explain that. Newton's laws explain all of Kepler's laws of motion. And they allow us to find the masses of objects if we can watch them moving around each other. So we can find the mass of the sun just by knowing that it takes Earth a year to go around the sun, and by knowing the distance between the sun and the Earth. We can find the masses of stars by watching them orbit each other. We can find the masses of planets by watching their moons orbit each other. And you'll, in your homework, you'll find out the equation that lets you do that. It's just a form of Kepler's laws as Newton derived them. And we won't be plugging numbers into those laws, but I will ask you to think about how something changes if one of the numbers changes. For instance, if I have two masses and one of the masses becomes twice as great, how does the force between them change? Well, if the mass is twice as great, the force is going to be twice as much. And you'll learn how to do that. So please read the introduction to Module 3. That will tell you all about that. Well, finally, this is a cool time to go outside and look around. I'm going to pull up Stellarium here. This is set for Monday. This is set for September 12th at 9 o'clock. And now the days are getting shorter. You can go out at 9 o'clock. And if you look toward the south, you get a beautiful view of the Milky Way. I saw it just coming up from my house the other day, very faintly, because I live, in Ogden, so I see the city lights. But if you go outside the city lights, you'll have a great view of the Milky Way coming up. Here's Sagittarius, the little teapot. Here's constellation Scorpius with the star Antares in it. Over here, the planet Saturn. And over here, the planet Jupiter in the east. Now, there's no moon in the sky because by this time, we're moving past the full moon. In fact, yesterday, Saturday the 10th, was the full moon. But by 9 o'clock, that means the moon has set and the sky is dark. So now, for the next couple of weeks, if you go out at 9 o'clock or later, you have a beautiful dark sky, and you can really take a look at the Milky Way and at the different constellations. So I hope you enjoy learning about Newton's laws of motion and gravity, and how we can use them to discover things about those lights we see in the sky. If you have any questions, you can always put a question in the discussions. You can send me an email. I'll be happy to set up a Zoom meeting. You can drop by my office and we can talk about things. But hope you have a good week, and I will look forward to seeing you next time. So, till then, take care. Bye-bye.